All right, so these rules, and make sure you guys are copying these down as we go along. These rules are not angle facts. These are kind of the algebra facts that we have to use. Now we're moving into proof. The general idea for today is don't get too caught up on the structure of what a proof is. We're going to develop that more and more, and I'll say that a few times. But we do need to have a few more rules that we use, and they'll make sense because it's stuff that's kind of you already know, except for a couple of these. So the first one we have is the reflexive property. And the reflexive property is a really strange property, and it basically says that a quantity is equal to itself. Alright, it might seem like a strange property to have because of course something is equal to itself. So here's an example of the reflexive property. You ready? 4 equals 4. Did I just blow your mind? Alright. And here's another one. Segment AB is congruent to segment AB. So that segment is congruent to itself, is equal to itself. Now again, this actually is used quite a bit when we get into our triangle congruence proofs. Until then, it's just kind of this random thing. It's like, why do we even have this? But you'll use it a lot, and luckily it's pretty self-explanatory. The abbreviation for this is going to be RP. All right, the next one. These next 4 are going to be properties that you guys are very familiar with. So we're going to start with the addition property of equality. And the addition property of equality, we're going to summarize this. We could make it way more technical, but we're just going to write it in a very simple way. You can add to both sides of an equation. Alright, so that's pretty straightforward. You can add to both sides of an equation. Kind of what's hidden in there that I'm sure you guys understand is that you're adding the same quantity. You're not going to add 1 to one side and 2 to the other side. So you can add the same quantity to both sides. I think it's understood well enough, so I'm not writing it down. And this abbreviation is going to be the add POE. All right, we're going to have other properties of equality. The next one, once you see the next one, you'll probably be able to guess from there. The next one is the, I've already heard it, the subtraction property of equality. So you might have learned properties like this last year. Did you guys learn, I know you learned the commutative and associative property, stuff like that, and you might have had to go through, kind of do some proof-like things when you were learning those. You might have even learned these properties of equality. I don't remember, but whatever the case, you already know these things. So the subtraction property says you can subtract from both sides of an equation. Okay, and here, now this one you'd think it's just sub POE, but we have to actually call it the SUBTR. So subtraction property of equality. fine. Now, go ahead and start writing the next one. These are all things that you already know, so I'm not going to spend too long talking about them. What do you think the next one's going to be? Man, you guys got it. And you can even guess what the next one's going to be, too, after that. There you go. So the multiplication property of equality. So, I mean, it is still useful to write this down just so that you're really connecting that knowledge and embedding it deep in those hardwire in your brain. So, property of equality. So, you can multiply on both sides of an equation. All right, and this one will just be MULT, property of equality. I'm sure some people are already working ahead to division. That's fine. I'll write in just a second, but I'll leave this up there for people who are still trying to copy. All right, the last two. So we have the one that we already mentioned, the division property of equality. I'll go ahead and copy all this down. Division property of equality, which says you can divide on both sides of an equation. And this will be div, division, property of equality. The very last one that we need to write, this is why we couldn't call it the sub POE, because we have another one, which is the substitution property of equality. Again, it's something that you already know, but it's a little bit different from the last four we did. Addition, subtraction, multiplication, division. It's just all the basic arithmetic operations saying that you can do those things. Well, now we're going to use substitution. So the substitution property of equality says a quantity may be substituted for its equal. And the abbreviation for this is going to be SUBST. So we have to make sure we distinguish between the subtraction and the substitution property of equality. And I'm going to go ahead and include an example of the substitution. It's one we've been using it. If you think back to that Bell work we've done where we've had to do a lot of substitution in order to solve for x in terms of z, that kind of fun stuff. That's the substitution property. But the example here is just a really basic one. If I've got x equals y, and I've got that x equals 5, well, I could just do some substitution to show that, therefore, y equals 5. Because all I'm doing is substituting y in for x. Right? Okay, so it's of these 6 properties we just wrote down, the 3 that you will use the most frequently by far are going to be substitution property, the subtraction property, and the reflexive property. Addition, multiplication, and division, we're going to use those today, but honestly, you might not use those very often or ever again after today. I mean, they could come up, so just be aware. But luckily, it's pretty easy. If you ever add things, it's the addition property. If you ever subtract things, it's the subtraction property. All right. So let's go ahead and, assuming you guys are good with this, let's go ahead and get started with doing our first proofs. All right. So with these proofs, I will mention this a number of times, but I just want to make sure it's really clear. Today, I want you following along with the logic of everything. And I want you to treat this the same way that you were thinking about logic puzzles. So when you have a logic puzzle, you have a starting point, which is whatever information they give you, and you know what your end point is as well. You're trying to, in the case of Sudoku and those logic puzzles, you're trying to fill in all the spaces until you've got it completed, right? So in a proof, they give you a starting point and an ending point, and the starting point is right here, given. The ending point is what we're trying to prove. Real quick, I'll have us fix a typo. The second one here should be not x equals 7, it should be x equals 5, and we'll get to that one in a minute, but we can go ahead and fix the typo. But it's important. I will tell you, the proofs that you guys are going to do, the prove statement, and that's what we have here. I'll go ahead and make a note of that. This right here, drawing a circle around it, this is called the prove statement. The prove statement will always be true. You just have to figure out how to show that it's true. All right, so you can think of this a couple different ways. Think of it like a logic puzzle, especially when we get to our main type of proofs, starting on Thursday is when we'll actually do some of those, I think. But those are called triangle congruence proofs. You can just approach these diagrams and think, okay, this is a puzzle. I need to figure out how to get my starting point to connect to my ending point. And you already have the rules you're working under because you know what angle facts you can use. Linear pairs, corresponding angles. So just from the perspective of how I want you to approach these problems, that's what we're talking about right now, just think of it like a logic puzzle. Here's the start, here's the end. How do I get there? And let me just kind of piece it together. The structure of the proof is something that we will work on, and the structure you're really going to need to know is for the triangle congruence. Not this so much. So at the end of the day, if you're like, I'm not exactly sure why we put it in that specific order, that's okay, because you're not going to be doing proofs exactly like this. So what we're going to do in order to kind of establish how a proof is written is we're going to start by just solving an equation. And that's what we've got here. I'm going to start, and we're only going to solve this equation, and we've got this T-chart. These are called two-column proofs, but we'll get to the second column. Let's just work on the left side only and solve our equation. Nothing super complicated here. I've got 2x minus 9 divided by 5 equals 1. I want to solve for x. What's the first thing I should do? Okay, I heard a number of things, but I think I heard the right thing in there. Multiply by 5 is what we should do. Yeah. So multiplying by 5. So if I multiply both sides by 5, I'm going to kind of show this in red real quick, just so you guys can see what we're talking about. That'll cause the 5 in the denominator to cancel out. I'm not going to leave the work for this, okay? I want to just show what the next step looks like. So we multiply by 5 on both sides, and we should end up with this statement. We've got now 2x minus 9 equals 5. Is that correct? Yeah. Okay, so what do we do next?
You should subtract 9.
Add 9. Okay. I was hearing a few people saying plugging in that x. We're going to pretend like that x, we don't already know that it's 7. Okay? So we can't just plug numbers in. So we're going to add 9. We're going to solve it like we would any other way. So if I add 9 to both sides, that'll cause the 9s to go away on the left. And I'm left with 2x equals what? 14. And then, finally, the last thing I'm going to do is?
Divide by 2.
All right, dividing by 2 causes it just to be x. And we got what we were trying to prove. X equals 7. So what we're going to do now is I'm going to number these lines. I've got the first line where I started, and then the second line, the third line, and this is only 4 lines, and then we're done. So I need to justify now everything that I did. And this is where you might have done kind of proofs, if you want to put that in quotes, proofs like this last year. I don't know. I know in the past whenever I taught algebra, we did stuff like this, but I don't know if you did or not. So anyways, we need to justify every step of the way. The first step is fine because they gave us that equation. We didn't need to prove that equation exists. They already gave it to us, so all I'm going to do is write given. And this is how we're always going to start a proof. They're going to give us some kind of information, and if you look at everything on this page, you'll see a bunch of given and prove statements. The givens, we're always going to write those down first. That's kind of saying, here's where I'm starting from, here's where I'm going to go to. So anyways, how did we go from the first line to the second line? We multiplied. So what are we going to justify this with? You got it. Multiplication, property of equality. The next one, we went from 2x minus 9 equals 5 to 2x equals 14. We added. So, what should line 3 say? The addition property of equality. All right. So, it's whatever operation we did to the equation, that's what we're showing. All right. We had to add, so it's the addition property. And then to get to our last step, what did we do? Divided. So you've got the division property of equality. So this is a proof. This is our first proof. It's not looking like what the rest of our proofs are going to look like, really. But we're getting the idea. I will say there is, by convention, we always end a proof with this statement. QED. And I'll explain that. So this is telling us to prove that x equals 7. We went through 4 steps and showed that x equals 7. So we just proved that which we were trying to prove. And QED means quod erat demonstrandum in Latin. You don't have to remember that. And this is basically Latin for that we were trying to prove. Which all it's saying is, you told me to prove x equals 7. I just proved x equals 7. That's what you asked me to demonstrate, so I'm done. Or that's what I said I was going to demonstrate. Now, for your purposes, you can just think of it like the exclamation point at the end to finish the sentence, okay? So write your QED just to show that, yes, I'm finished. I have nothing more to add to this. All right. Easy enough? All right, we can do another one, but let's do this at the same time. We're going to do the left and the right, not just solve it all at once. So, first step right here, what are we going to write? Given. All right. And our given here is that equation, so I'll go ahead and copy that down. 2 times x plus 5 equals 20. All right, what are we going to do next? All right, now I know some people are looking at this and thinking, oh, that's distributive property. And it is kind of, but we're not going to use the distributive property here. So yeah, we'll do what Mikkel was saying. We're going to divide by what? 2. If we divide by 2, then we get rid of that 2 out in front of the parentheses anyway. So I will divide by 2. I'm not going to show the algebra. You'll kind of have to do that in your head. So x plus 5 equals what? 10. Because of the division property of equality. And now, what are we going to do? Subtract 5. So x equals 5 because of the subtraction property of equality. And we finish off our proof with QED. You'll get used to doing that because you'll do a lot of proofs. Okay, so there it is. It's just our way of justifying every step. Say we have a rule that tells me this is one of the properties that I'm allowed to use. So I'm going to invoke this rule of subtraction property that says I'm allowed to do what I just did. Okay. So a lot of, not just a lot, but all of our stuff moving forward is not going to be algebraic proofs, but it's going to be geometric proofs. And that means here we have a diagram. This is a kind of geometric proof which I call an angle proof. So we're proving that certain angles are congruent or supplementary or something like that. Again, the kind of proof you're going to be tested on, that you're going to need to know really backwards and forward, is the triangle congruence proof. And it's not, if that sounds complicated, it's actually, you'll learn the structure, it's not bad. So anyways, we've got this diagram, and what we're trying to prove is that measure of angle B plus the measure of angle C equals 180. All right, let's go ahead and just start writing the proof, because we can write the first line. The first line is going to be what? Given. And what is my actual statement going to be on the left? Yep, there it is. All it says is diagram, so that's what I'm going to write down. So here's what I like to do, and this will make sense here in a minute. I don't want you to get too caught up with exactly how to write a proof for something like this, but I just want you to follow along with the logic. I'm trying to prove that measure of angle B plus the measure of angle C equals 180. So I'm going to go over to my diagram real quick, and I'm going to show, well, here's measure of angle B, here's the measure of angle C, all right, and I'm marking it on purpose, and I'll show you why. At this point, we have to use a little bit more logic. Just start looking for any angle relationships you know in this diagram and tell me what you can see. It's same side interior. So we have same side interior right here. So I'll go ahead and show that those two are same side interior. What else do we have? Vertical angles. So I'm marking these in different colors. Hopefully you can see them. If you need to turn the lights off, you can. What do you guys think? Lights on or off? Off. Go ahead. Can you turn them off?
Save electricity bill money.
Okay. So this helps you see the different colors a little better. And this is, again, just for today's purposes, we're going to know we're done when we've got two arcs on every angle. So B has been marked twice, A has been marked twice, C has been marked twice. So I know I've found enough information. We have same side interior angles, so let's start with that one. So we need to say something about those same side interior angles. Here's what I'm going to do. I'm just going to write that down. On the right side, same side interior. Now what equation can I write down as a result? Measure of angle C, plus the measure of angle A equals 180. Perfect. And I'm going to underline this one in red because that's what I marked it with, just so we can keep that color coding going on a little bit. I know you guys don't have color, so this is just to see the logic up here on screen. Number 3. What can we say next? The vertical angles. We also found those. And what can we put as our statement for vertical angles? Measure of angle A equals the measure of angle B. You can see why we're not just moving on from those angle facts. We're still going to be using them daily. So you need to keep those in mind. Okay. So I'd say we're ready to prove that measure of angle B plus the measure of angle C equals 180. How are we going to do that? Any thoughts? I'm going to go ahead and write it down. So measure of angle B plus the measure of angle C equals 180. That's exactly what I was trying to prove. Now, how can I justify that line? I can't just put it there and say, oh, because. Because, ... That's not an acceptable proof. So looking at these two equations, I can do something with, I can manipulate these two equations in lines 2 and 3 to come up with the fourth line.
Corresponding angle.
It's not an angle fact. Now we're moving to our algebra facts. Did we add anything? Say that again. Substitution. We just substituted. Remember I said substitution is going to be used probably more than any other property here. So substitution is going to be used all the time. And yeah, we've got that A equals B in line 3. So what I'm going to do is I'm just going to take B and substitute it in for A. All right, I'll show that, but that basically gives me my proof statement, doesn't it? Yeah. Okay. So I need to justify this line with what you guys just said. This was a substitution property of equality. And that gives me my final answer, QED. Okay, let's see if we can write this next proof a little faster. The nice thing about the next one, before we do that, any questions on this? Okay. The nice thing about the next one is that you have all 5 lines of the proof. You know the proof is 5 lines long. And we can go ahead and start filling this in. So the first line is going to be diagram given. We also know where our proof statement's going to go. Where is it going to go? The very last line. So the measure of angle X equals 123 minus 76. Okay, now here's how we know that that's going to go there. Our proof statement's always the last line, but think about it like a destination. We are starting somewhere and we're working toward this line. If we get there, why would we keep going, right? If it's an actual destination you're traveling to, if you get to your destination, you're not going to keep traveling. You're there. You stop. So that's what we're thinking about. Once we get to the proof statement, we're done with our proof. All right. So we're trying to show that 123, I'm going to mark these angles, 123 minus 76 equals X. What other angle relationships do we have in this diagram? We've got corresponding angles right here. And we've got exterior angle of a triangle. Now, has every angle been marked twice? Yeah, it has. So that's all we need to know. So let's go ahead and write down, it doesn't matter which one. You guys said corresponding angles first. So what is my equation going to look like for that?
X equals Y.
All right, so I'm going to write as the measure of angle X equals the measure of angle Y. And we know that they're equal because they are corresponding angles. Remember, the type of angle relationship it is determines what the equation looks like. Okay, what's our equation going to look like for the exterior angles? There you go. Measure of angle Y plus 76 equals 123. All right, so this is, imagine this is a proof and I was grading 1 point per blank. Hopefully, if you could get this far, you got 7 out of 10. That's pretty good. This is where maybe it gets a little bit trickier, but you guys should be able to work from here. What do you think we're going to do in this next line?
Subtraction.
Okay, and we could do substitution or subtraction first, but let's do the subtraction. So what are we going to subtract?
76.
All right, notice we're trying to prove that an angle is 123 minus 76. So I'll go ahead and subtract that 76 from both sides. And if everyone agrees, we're going to have an equation that looks like this. Measure of angle Y equals 123 minus 76. Does that look right?
Yeah.
And that is subtraction. And so I'm just going to go from this equation where measure of angle Y equals that to this measure of angle X equals that. How are we going to get from Y to X?
Substitution.
Substitution. Well, we've established right here in line 2. This is another reason why you number your lines. You can say, look back in line 2, we showed, now it's really easy for everyone to find that x equals y, so I can just substitute x in. So you can see right here, we went from subtraction to substitution. This is a classic kind of move here where you do subtraction and substitution. Anyways, we're finished. We write QED. Does that logic make sense? Okay. So we've got enough time to finish this, luckily. Now, you might wonder, why did we leave this as 123 minus 76? Why didn't we just do the math and get our answer, 47? Well, it'll make... What's that? Yeah, that's not what they asked us to do as a proof. And also, you're going to see, I think this is the last proof we do where we're working with specific numbers, except for 180 degrees. So we're going to do this same proof again. We can basically copy it down with a couple of substitutions. And notice in the next one, it's the same thing, but we don't have 123 and 76. We've got C and D. All right, and let me explain why we're doing this. With this proof right here, we proved a very specific case. We proved that when this angle is 123 and this angle is 76, that x is going to equal 123 minus 76. With the next proof, what we're saying is this is a generic case, meaning we don't know what angle C and D are, but the diagram is set up like this. So now we can say no matter what C and D are, x is going to equal this angle minus that angle. So we're going from a very specific case to a generic case. Does that make sense?
Yeah.
All right, so luckily we can kind of copy the proof down again. The first line's the same. We've got diagram and given. You guys noticed the corresponding angles. I'll go ahead and mark these things again. Or let's go ahead and start with our proof statement. That's what we wrote. So the measure of angle X is going to equal the measure of angle C minus the measure of angle D. You guys noticed corresponding angles. And the equation there, actually this equation doesn't change at all. Measure of angle X equals the measure of angle Y. I'm doing this quickly because it's a copy of what we did before. The next thing you noticed was exterior angles of a triangle. Okay, so we've got exterior angle of a triangle, and tell me what this equation is going to look like now. Measure of angle Y plus the measure of angle D equals the measure of angle C. Okay, the next thing we did in the proof above was what? Okay, yeah, we did that subtraction, so now we're going to have the measure of angle C minus the measure of angle D. So same as before, but now we're dealing with a generalized form of this where it's just C and D. Okay. And we can now show the final proof statement because what property did we use? Substitution. We just substituted x in for y. All right, so what we have here is a proof that's finished. And you might wonder, why did we care to do this? All right, what we have just done here is we have just created a theorem. So forever after this, we can say that anytime we have this exact diagram or this exact angle relationship, you could look at this and you could call this whatever you want. You could call it exterior angles and corresponding angles theorem, because that's kind of what we're doing here. But basically, anytime you see this setup where you've got parallel lines with a triangle right here and these two angles and this one, you always know that this angle is going to equal C minus D. Now, this isn't a very useful theorem, you can tell, because you're not going to come across this diagram very often. But this is technically a mathematical theorem that this will be true no matter what, anytime you see a diagram set up basically like this. So it's kind of useful, maybe. But with theorems, we can come up, or with proof, we can come up with all kinds of theorems that now we can take this theorem and we can apply it. Let's say there's another diagram where we extended this even further. We could say, well, because of the exterior angle corresponding theorem, well, now we know that this equation will be true. And I can substitute some work in. So it's a way of kind of building up math to get to more and more complex ideas. Does that make sense? All right. So when you get into hardcore, real mathematician type math, they're doing proofs all the time to try and build up our understanding of the limits of math and what it can do. So that's kind of the idea of proof. And we're just scratching at the surface of it with what we do here. But it's important from one perspective of just understanding logically how we can get from a starting point to an ending point. And hopefully that makes sense a little bit. But we're going to stop right there for today.